Got to click all the buttons. Okay, so here is my short take on chapter 4. Hopefully it's still somewhat review from your Gen Chem or like your prep chemistry class or high school chemistry, if you took that. And really, this is the one where we start looking at chemical reactions. And if this is review, then there'll still be some stuff that I think that's a little bit harder than any like chem prep class, which will be like the solution stoichiometry piece and the titration piece. So basically this chapter kind of breaks down from chemical reactions into a few things. One, it's like we have to first figure out how to write them and balance them. Then we go through stoichiometry, which is that big word for like predicting the amount of a product you'll actually make. And then kind of within stoichiometry, there's some other pieces. There is limiting reactants and percent yield. And then also in this chapter, then we go into solution stoichiometry. And it's the same principle, it's just going to include molarity in the thing. And within that, we also can then talk about titrations. And that's what our lab 3 is going to be about this week, which will be fully online, so you won't need to use your lab kit. We'll do a titration in chemistry 162 using lab kits with like pipettes. But this is to get us familiar with the calculations around it, so that way when we do it, it's not like the end of the world. Okay, so that's like a really big chunk of the math part of this, but then there's like a third part, which is the different types of reactions. And there's a few different like categories within that. There's going to be, get rid of these pictures. I'm actually going to make that really small. There we go. So within these types of reactions, we have acid base, gas evolving. We also talk about the precipitation reactions. These are also called double replacement. And we do redox reactions. And within these, the like part of the idea is just to like identify the general types of reactions, but like the redox reactions and the precipitation reactions are the ones we focus on and we do a little bit more with. So like within redox reactions, we have to learn about oxidation numbers. And then within, and identify what is a reactant and what is an oxidant. Probably with an A, not an E. And then with precipitation reactions, we're gonna talk about like net ionic equations and write those, which is like just focusing on the things that are changing within the reaction. We also have to review solubility rules. And you'll be predicting products for this one. So it's a lot. It's kind of, it's a lot. It's kind of a broad swath of information. Oh, that's someone else in. So, and welcome to those that just joined. I'm recording, just a heads up, and I'm just kind of walking through an overview of chapter 4 and then taking questions. So I'll go for a little bit. I'll do like kind of one section, then we'll stop and then we'll do the next and go through that. So let's just start with number 1, which is like the writing and balancing of chemical equations. In particular, this one I kind of hope you've seen. So some of my goals for this part of the chapter is I'd like students to be able to interpret like a procedure or a description of a chemical reaction into a chemical reaction, like written out. So interpret a procedure into a reaction. And go the other way too. And so basically it's like when we write a chemical reaction, what is that plain English version of it? So for something like, let's do sodium solid plus chlorine gas to sodium chloride solid. So like, here's the chemical reaction. And then the plain English version of this is sodium solid and chlorine gas react to form solid sodium chloride. And like, you could write that in a longer or a briefer way. So that takes a little bit of practice. After that, it's really about balancing reactions. I guess I should highlight real quick that things that are important are the phases in these chemical reactions as well, and that arrow. Sometimes I get a lot of equal signs instead. Please use an arrow. It's just like a pet peeve because the arrow like implies before and after, whereas an equal signs like implies equivalent. And the equal sign will get confusing when we start doing equilibrium because it'll look like the forward and reverse arrow that we'll use for that. So for balancing reactions, we really just want to make sure we have the same number of atoms on both sides of the arrow. And my recommendation for this is to practice, but also I would focus on one atom at a time. And only tally everything at the end. And the reason for that is because there's a lot of like simple mental math errors that occur when you're balancing reactions. Like you just like add 2 + 3 incorrectly, right? We all do it. It happens all the time. But if you're telling all of the different atoms after each like time you balance one element, you open up yourself to a lot more possibilities for making a small mistake that then makes the problem not solvable. And so it also just takes a lot more time. So if you just try to balance one element at a time, then you can at the end make sure everything works out and it'll go a lot faster and you tend to make less mistakes. And that's basically it for kind of that first part. And I think everyone's going to kind of come in at different levels with this. And if you need a little bit more practice, like just practice balancing reactions until it's something that comes quickly to you. So at this point. All right, stoichiometry, it's that big word. So really this is about predicting the amount of something that you'll form. And sometimes it's products, sometimes it's actually how much reactants you need to use. Yeah, so you might go kind of lots of different ways, but in general, like we use this tool to predict the amount of something that will form. So there are a lot of little algorithms that exist out there for solving stoichiometry problems. If you've been taught like a method that you can reproduce over and over again, great, just do it. And I'm going to show you like one way that I found that seems to simplify things for looking at limiting reactant problems, but like overall, I don't think that any of the different kind of methods of solving this are better or worse than one another. So if this doesn't work for you and you want some more suggestions, let me know. And I can show you a few other ways of solving it. And it's all the same problem solving strategy. It's just like how you order the problem solving steps and at what points you do a comparison. So That's my big asterisk there. So for a lot of these, what we first start with is mass to mass conversions. And so what we'll be doing is we'll be taking the mass of something that's known, converting it into the number of moles, and then into the moles of something that we are curious about, and then to the mass of that thing we're curious about. The conversions that we're going to use are molar mass, which will equate grams to moles. And we're going to use mole ratios. And these come from our balanced equation. So I'm going to just take that one that we were talking about before when we were writing out an equation. We had sodium solid plus chlorine gas forms sodium chloride solid. So when we look at this, just balancing it right off the bat, we have 2 chlorine. So we need to have 2 chlorine on our product side. That makes us have 2 sodium. So we'll have 2 here. So now I have a balanced equation. So that's always the first step. So that balanced equation can be then interpreted into a set of conversion factors. It means that 2 moles of sodium equal 1 mole of chlorine gas, which will equal 2 moles of sodium chloride. So I can use this as a mole to mole conversion factor. I can also calculate the molar mass then of each of these. So the molar mass of sodium is, it's something. It's about 11, I think. No. And then like when in doubt, just like Google it, right? I guess you should always have a periodic table handy. So the molar mass of sodium is 22.9898 grams per mole. And you can think of that grams per mole, remember, as 22.9898 grams equals 1 mole of sodium, right? So that's written as that equality, kind of in our dimensional analysis style. So our chlorine gas is going to have a molar mass of 69.938. And the molar mass of our sodium chloride is going to equal 58.44 grams per mole. So usually these questions are structured so that it's like, you have some amount of this reactant, how much product forms? And I know whenever I read them, I feel like I just don't have enough information. And that's always my red flag that I have to do a stoichiometry problem, because it requires you to build your own conversion factors. Right? So you have to remember to actually do that. All right, so I'm going to walk through a limiting reactant problem rather than just a straight stoichiometry problem as an example. So stoichiometry problems are when you know information about one of your reactants or products and you're predicting about another one, and you have lots of the other compounds around. So that way you know that like your limiting amount, the amount that'll predict the product or the reactant, is the one that you know about. Sometimes though, you'll be given information about, let's say, both of your reactants, like you have this amount of sodium and this amount of chlorine gas. And so you have to first decide, well, which one do I have the least amount of in this chemical reaction? Like which one will predict the products, because it'll run out and then I'll have excess of the other one. And like, there's lots of analogies for this, but like the one that always comes to my mind is like hot dogs and hot dog buns, right? You get, I think like 10 hot dogs in a package, but you only get 8 buns in a hot dog package. And so if you buy both of those, the only the buns limit the amount of actual full, complete, delicious hot dogs that you can actually barbecue. And so it's going to be the limiting reactant would be the buns, because you have 8 and you have 10 hot dogs. So by the time you make 8 hot dogs, you're going to have 2 leftover hot dogs without buns. And so that would be, the hot dogs would be in excess. All right, so let's just do something here. So let's say we have 1.0 grams of sodium and 1.0 grams of chlorine gas, how much sodium chloride is formed? So the question would be asked something like that. And so the information that we have is just 1 gram of each. So to determine the limiting reactant, I recommend just calculating the amount of product for both and seeing which one is less. You can also just calculate the number of moles of the product that forms and then see which one is less, and then you'll know which is the limiting reactant. But the idea is that we can't directly compare the masses of the reactants because it's not about the mass that we have, but the number of molecules or atoms, because they're going to collide to form a product. And so we need to compare the numbers that we have and also then take into account the ratio they're going to react in. So the way I handle these usually is I'll just like start with, let's go like this, 1.0 of my sodium grams. I always write out the units to help me with this, so I am confident that I set it up correctly. And I usually put the chemical formula following that. So let's use our molar mass. We're going to go from, again, remember, we're going to go mass to moles to moles to mass, essentially. So we're going to convert to mass using our molar mass. So we have 1 mole on top and 22.9898 grams on the bottom. So and this will be a mole of sodium. So these are going to cancel out here, right? And so this first step is converting mass to moles for the sodium. Then I'm going to convert into the moles of my product, which is that sodium chloride. And I'm going to use that equality from my balanced equation. So I know that I'll form 2 moles of sodium chloride for every 2 moles of sodium that react. And that's just coming from that equality I created from the coefficients. So that's 2. So this is moles of sodium being converted into moles of sodium chloride. And then we're going to convert into the actual mass of that sodium chloride, which is going to be times the 58.44 grams of sodium chloride divided by the 1 mole of sodium chloride. And then 3, we're going from moles to mass, using that molar mass. And doing all that will get us a calculation for our product, which I'll like plug in here. And I'll pause and see if there's any questions at this point while I'm doing that. All right, so we get 2.5 grams for our sodium. And then what we would basically do is then just walk through the same thing for the chlorine gas. So I'll set that up a little bit faster. So we have 1 gram of chlorine gas, and then we'll use our molar mass conversion to get into the moles of it. So 69.938 grams. Then we'll do our mole to mole conversion. We'll form 2 moles of sodium chloride for every 1 mole of chlorine gas. Woo, there we go. And then we'll convert into the sodium chloride again. So you can notice this last step is like the same on both of these. That's why you can kind of stop after the mole to mole conversion and compare those, and you'll get the same, like you'll come to the same conclusion. So let me just do this really quick. The next step at this point, once you have 2 numbers, is to actually compare them. And whichever one is smaller will be the amount that forms from the limiting reactant. So you won't be able to, so this is 1.67 grams. So we're going to compare. And this one's smaller. Therefore, this is the amount we form. Which means our chlorine gas is our limiting reactant. So I would report that we form 1.67 grams, and then we have some leftover sodium. And I can calculate that. I can figure out, well, if 1.67 grams forms, like what's the mass of sodium that actually reacted to form that, and how much sodium is left? So yeah, there's lots of that you can do with it. So that's a limiting reactant problem. The other kind of piece we do with stoichiometry is going to be percent yield, which is just a ratio of like what actually forms versus what you predicted. So it's like the actual amount that you like isolate when you do this in the lab versus the theoretical. And that theoretical amount, that's what you calculate in a stoichiometry problem. So your stoichiometry answer equals your theoretical. All right. So the other piece within this then is once we kind of have stoichiometry down and limiting reactants and percent yield is solution stoichiometry. Solution. Which we use in titrations calculations. Solution stoichiometry is like the same problem solving strategy. The idea is you have some amount of something known and you're converting through moles to calculate some unknown. The trick is that instead of using a mass to mass conversion, you might be using concentration and volume. So if I want to calculate, let's look at these two. So molar mass, right, is going to be like the moles of something. Here, let's do it like this. So to calculate the moles of something, I could do either the mass of, let's call it A, times the molar mass, which would be 1 mole, or the inverse divided by the molar mass, grams of A, would equal the number of moles. Another way to calculate moles is if I know the volume of A and I multiply it by its concentration. And so that's the real difference with a solution stoichiometry problem. Let's say that my chlorine gas, well, let's do it like if my sodium chloride was gonna, no, that would explode if it was in water. Be like, I chose an example that like doesn't lend itself to switching to solutions very well. But basically, if I had, it's like equivalent to saying if I start with 5 grams of hydrochloric acid, how many moles would that form? Or I could say I have 5 milliliters of a 1.5 molar. Let's do it like this. Yeah. Solution. I can use that to find the number of moles too in my stoichiometry problem. So same strategies, just use the concentration stuff from chapter 3. For titrations, you can just do this like a solution stoichiometry problem. So it's the problem solving strategy where you're like, okay, I'm going to convert my volume to moles using concentration as a conversion factor. Then 2, you convert moles to moles using coefficients. And then 3, you convert your moles of, like, let's say it's A to B, right? Of B to concentration by dividing by the volume. So there is this thing that big if your mole to mole ratio is 1 to 1, then that step 2 is really just multiplying by 1, which means you can kind of skip it, right? And so then you can use this idea of MAVA equals MBVB, which is the concentration times the volume of the acid. equals the concentration times the volume of the base, which is really just combining steps 1 and 3 above. And it really only works if you have that 1-to-1 mole ratio. So if you don't, and you use this equation, it won't give you the right answer. So like, big warning. So a lot of us learn that as like a quick method of doing titration problems, but then it becomes a problem later on. All right, I will pause there and see if there's any questions. Okay, let's look at like kind of the next part of this, right? So our types of reactions. So my expectations for this section is really a couple-fold. One, I'd like you to identify different types of reactions. And it might be helpful just to kind of create like a list of like kind of like red flags for each type, like write them on a note card or something and keep them handy. So the ones that we're kind of focusing on are acid base. And we're just really showing you neutralization reactions right now. We will spend so much time on acids and bases. I spelled that wrong. And so this is really just an introduction to it. And so these will usually produce, so the products will be water and salt. That's how I recognize them. Then we have gas evolving. These ones are easy. You have a gas phase product that wasn't and not in the reactants. So it like makes a gas. There's combustion, which usually produces CO2 or CO or carbon, depending on the amount of oxygen around, plus water if the products are hydrocarbons. And so if there's CO2 and water, then it's usually a combustion reaction. The other piece is that oxygen is a reactant. All right, then there is precipitation reactions or double replacement. And I noticed these ones because you'll have aqueous reactants and something will form a solid as a product. And then lastly, we have redox reactions, which stand for reduction and oxidation. And these reactions, both of those things occur. And these ones are kind of like, if it's none of the other ones, then I check if it's redox. And usually what you'll see or notice here is there'll be a change in charge or oxidation number between reactants and products for an element. So actually, like this combustion type, this is actually a type of redox reactions. And a lot of gas evolving ones are also redox reactions. Yeah. All right, so those are kind of like my personal like red flags or like things I try to remember when I'm like trying to decide what type of reaction something is. So getting familiar with them is really helpful. So that's one piece of this. And then within it, we're going to focus on two of the types of reactions. We're going to focus on these double replacement or precipitation reactions and redox reactions. So we'll go into those. So for precipitation reactions, I expect that you can predict the products. And the product's chemical identity, and then also the phase. And for this, you're going to need to, for the phase part, you're going to need to use a solubility chart, which is in your book and the lecture notes, hopefully. Yes, definitely. So you're always going to have to kind of like reference that. You can memorize the solubility rules, but like it doesn't seem worth it. I mean, I remember memorizing them, but it was like annoying. So with the predicting products, what you're always going to do here is you're going to swap the ions essentially. So in a case where you have let's do like, so barium, and it's aqueous, so it's going to be like +2. Okay, let's do it like this. So like barium chloride, BaCl2, plus sodium sulfate. So these are both aqueous in the beginning. What we're going to do is we're basically going to take the cation and anion from each and combine them. And then predict what ionic compound would form when you combine those elements. And so that would be sodium plus ions and chloride ions. And I've got 2 of each. So that's going to equal sodium chloride. And then I'm going to also have barium +2 and sulfate -2. That's going to equal barium sulfate. So now what I do is I check and see, are either of these insoluble? And it turns out that in fact, the barium sulfate is insoluble in water, so it'll be a solid. And the sodium chloride is soluble, so it'll be aqueous. And so I can go ahead and then write this out again. So the kind of like full total reaction would be barium chloride aqueous plus sodium sulfate aqueous forms 2 sodium chloride aqueous plus barium sulfate solid. And then for our net ionic equation, it's just going to be the things that are participating in the reaction. So I can see that if all of these are aqueous, it means the ions are just kind of floating around everywhere. So the sodium ions and the chloride ions are just floating around in the reactants and in the products. So they're just doing nothing. So we call them spectator ions. So here our sodium and our chlorine are spectator ions. So that means that I really will have just my barium +2 aqueous plus my chlorine, or sorry, plus my sulfate -2 aqueous forms barium sulfate solid. And that would be my net ionic equation. All right, I'm going to pause here and see if there's any questions before I do redox. All right, lastly, let's talk more about redox. So redox stands for reduction and oxidation. These are like the best reactions because it's really about electrons moving around, which if you think about your body, it's just shuttling electrons all over the place. And a lot of the really cool chemistry out there is just shifting electrons around. So it stands for reduction and oxidation. So reduction is gaining electrons. And oxidation is losing electrons. The other way that you'll see these written, and these are the ways I don't like, but I know that Chem 101 uses it really heavily, is that something that is reduced acts as an oxidizing agent. So like if reduced, acting as. And what's really, this means it's like you can't have a reduction without an oxidation. Something that gains electrons forces something else to lose them. And so it's like a matter of perspective, right? So from the perspective of the thing gaining electrons, it's being reduced. But from the perspective of the other chemical, it is that thing is oxidizing it, right? So it's acting as an oxidizing agent. It's forcing something else to be oxidized. So you can use either term. You can either use reduced or oxidizing agent. Those mean the same thing. And I hate it because like with someone with this like mild dyslexia, like if we use the same term and flip it, like even if we're adding the agent, it's like really hard to follow. So I tend to use the one that's just reduced or oxidized, but you will see the other version. And then, so for oxidation, if something is oxidized, it's acting as a reducing agent. So something that loses electrons forces something else to gain electrons. So its agents, it acts as like a thing that forces reduction. And that's where those terms come from. There's like a couple ways to remember these. I always forget them. And I will honestly say I just like write it on my hand if I'm really desperate. But there's like oil rig is one. So oxidation is loss, reduction is gain, and it's referring to electrons. So that's one way to remember it. And there's like Leo the lion says grr. But like I can't remember what that, like I don't remember what it's like. Yeah, I don't know what it is. Sorry. Like everyone says that one, but I'm like, yeah, but I don't remember what the thing stands for. Anyway. Okay, so what I'd like you to be able to do with redox reactions is identify what's being reduced and oxidized. And I'd like you to write the half reactions that focus on them. We are going to do balancing of redox reactions in chapter 17 in Chem 163, I think. Bye, Natalia. And so like, we'll do that some more, but it's like worth reviewing now if you are familiar with it. So let's take a really basic one. You can have like, let's do what we were doing. Let's do. Let's not do that. I made this up. I don't actually know if this actually happens. So looking at these, I'm going to evaluate the charges on them. So my magnesium here is a +2 ion. My chlorines are -1. And this is all coming from that chapter 2 ionic compounds material. My sodium is the element, so it's got a 0 charge. And then in the products, it has a +1 charge because it's paired with chlorine now. So it becomes ionic. My magnesium has a 0 charge. So looking at these, one of them is going to be losing electrons and one is going to be gaining electrons. Looking at my sodium, it's going from a 0 charge to a +1 charge. Because it's gaining positive charge, it's losing electrons because it's losing that balance between protons and electrons. Like protons are winning, essentially, so it's positive. And then our magnesium is going from +2 to 0. And so because that positive value is decreasing, it means it's gaining electrons, which is a little counterintuitive just in the language of it. So that means that our magnesium is being reduced and our sodium is being oxidized. And this is a simple version. And our chlorine isn't changing. So it's not actually participating in the redox part. So really it means that sodium is giving electrons to magnesium. We can write the half reactions for each. So our magnesium +2 gains 2 electrons to become just plain old magnesium. And that what I'm doing here is I'm balancing my charge. So that +2 from the magnesium plus the -2 from the electrons equals 0, which equals the charge on the magnesium on the product side. And so this is my reduction half reaction. And then I have my sodium forming sodium +1 plus 1 electron. And this is my sodium, or this is my oxidation half reaction. So like it's pretty simple. I think when it's ionic compounds, like it seems a lot easier to me, but it gets harder when you're looking at something where you're like, I don't know what the charge on any of these things are. They're all covalent molecules. So then you have to use oxidation numbers. And they help us track like how things change and where electrons are, but like ultimately it's a bookkeeping method. It's not like an accurate picture of what's really happening, but it helps us make predictions. So that's cool. So there's a list of rules. You can memorize them. You can also keep them handy. And there's a set of rules that are in order of priority. And that piece is key. Like you have to like apply the rules in order of priority, because usually the last element won't be able to follow the rule. And ultimately the idea is if you have a neutral molecule, you need to have all of the oxidation numbers add up to its charge. So if it's neutral, that's 0. If it's a -1 ion, then it adds up to -1. So let's do something like C3. Oh no, let's make it a little simpler. To CH2O. All right. So let's figure out what the oxidation numbers are for each of these elements. So based on my order of operations, I'm going to have my oxygen first. It's usually going to be -2. Then if I keep going down my list, hydrogen is +1. And then carbon is way down the list, right? So it'll be +4 if nothing else, or it'll be used really here to balance out the charge. And so overall, this is 0. It's a neutral molecule. So I'll go through these in order. So first, oxygen will be -2. And then each of my hydrogens will be +1. So at this point, I have -2. And then I have 2 +1s from my hydrogen. So that's +1 times 2. So I'm at 0. So that means my carbon charge is going to be 0 in there. I can do a different one too. What about let's do SO4 -2, right? So in this case, my overall charge is -2. So everything needs to add up to that. In terms of order of priority, oxygen goes first. It'll be -2. So I'll have -2 for each oxygen. So that's -2 times my 4 oxygen that I have, which is -8. So to balance this out, my sulfur is going to be plus this -8 has to equal -2, right? So I'm kind of creating a little algebraic expression to help solve this. So that means my sulfur is going to be equal to +6. So my sulfur oxidation state is +6. My oxygen oxidation state is -2. And so then I could compare that to like the oxidation states in the product side and see if they change. And that would tell me if it's being oxidized or reduced. And that's oxidation numbers. So I'm going to stop the recording.